Dear students, welcome to the third lecture of open channel flow. In this lecture, we will be discussing the conservation equations for open channel flow. We of course begin with the most basic conservation equation, that's the mass conservation equation, or better known as the equation of continuity for open channel flow. Now the equation of continuity for a steady uniform flow or gradually varied flow or rapidly varied flow of an incompressible fluid is quite straightforward. We normally deal with water, the flow of water in open channels as civil engineers, and so the fluid is of course incompressible fluid of water. And for the equation of continuity for such a flow is given as Q equal to A1V1 equal to A2V2 as shown in the first equation of this slide, where A1 and A2 are the cross sections of flow at two different sections, and V1 and V2 are the corresponding mean velocities at those sections. Remember that steady uniform flow, gradually varied flow, or rapidly varied flow are those flows in which no flow is added or abstracted from the main flow. So the equation of continuity is given by such a simple one. For spatially varied flow, however, where the flow discharge is not constant at various sections, and remember that in spatially varied flow the flow becomes non-uniform due to addition or abstraction of some flow from the main flow. So if we consider that for a spatially varied flow, the rate at which the flow is added or abstracted, it's given by Q star is equal to dq by dx. Then the equation of discharge or continuity can be given at a section which is at a distance x from section 1, can be expressed as the last equation of the slide, qx equal to q1 plus integration 0 to x q star dot dx. So this is equation of a steady equation of continuity for a steady spatially varied flow. Now from the equation of steady flow, let's move on to equation of continuity equation for unsteady open channel flows. Now the continuity statement for unsteady flows, as we have discussed many times before in our lectures, that the continuity statement of continuity equation says that the net mass flux through an elemental control volume in the flow equals to the net rate of change of storage of fluid mass in that control volume. So this is the statement of continuity for a transient or unsteady flow in open channel. So to analyze the unsteady flow in open channel, let's focus on the diagram here at the top. So this diagram shows a longitudinal section and a cross section of an open channel. You can see that the cross section is that of a arbitrarily shaped open channel where an element has been taken at the surface. The element is of elementary cross section dA, which is equal to the top width given by capital T into the thickness of the element, that is dy. So that's the elemental area of the element. And on the in the first figure on your left, you can see in the longitudinal section the length of the element is delta x. So you can also say that there is a flux of flow. There is a flux, incoming flux of Q1 into the section 1, and there's an outflux of Q2 at section 2. Now, before actually deriving the continuity equation for open channel, unsteady open channel flow, let's discuss that what actually happens when the influx and outflux through an element are different. So if we consider that the outflux or the discharge which is going out of the element is higher or larger than the volume influx that is coming in the element, so of course the net storage of mass inside the element will decrease, and the decrease of the storage mass will actually result in lowering the water surface, as is shown in the diagram on the left, that at instant t, let's say at an instant t, small t, the water surface was given by the bold line, and due to the transient flow or the disbalance in the incoming and outgoing fluxes, the water surface has been at time t plus delta t has been lowered to the new surface, which is shown by the dotted line. So that's the theory of continuity that we are going to follow in the derivation of this continuity equation. Now the mass inflow into the element, into the elementary volume during time delta t, that's the time duration which we are taking into account, time delta t. So the mass inflow during time delta t is given by equal to m1 is equal to rho into q into delta t. And similarly, the mass outflow from the element in time delta t is given by m2 is equal to rho into q plus del q by del x into delta x, this whole multiplied by delta t. So we are considering an incremental increase in discharge along the longitudinal direction. Now the net decrease in mass in the element during time t, that is the rate of change of the storage of mass inside the element during this time is equal to delta m, that is given by m1 minus m2 which equals to minus rho del q by del x into delta x into delta t. Now this decrease in mass, actually we are going to equate it to the rate of change of mass of fluid in time delta t. So if the mass of the fluid in the element is equal to rho into capital T into dy into delta x, then the rate of change of the mass in time delta t is given by del by del t in the bracket rho into capital T into dy into delta x. So this is the rate of change of storage mass inside the element, and if we equate that to delta m, then we have 1D continuity equation for an unsteady open channel flow, which is given by the last equation on the slide, and which is given by del q by del x plus capital T into del y by del t. Now from the equation of continuity or equation of conservation of mass, let's move on to the equation of conservation of momentum or momentum equation for open channel flow. We know that momentum is a vector quantity, of course, and we also have discussed many times that equation of conservation of linear momentum is a mathematical statement of Newton's second law. Uh, in the derivation of momentum equation, we consider a control volume, as we can see in the figure on your right hand side, that the control volume has been indicated by the dotted line. You of course know that control volume is a volume inside in the flow regime on which we analyze the forces and momentum of flow. So the control volume has been taken like this rectangle or square, whatever, and the forces on it has been shown by the arrows. Now we can see that on the left hand side of the control volume there is this force F1. F1 is the hydrostatic force which is working on the left, and F2 is another hydrostatic force which is working on the right hand side of the control volume. So these are surface forces. There is another surface force which is given by F3, which is nothing but the resistance or the shear resistance offered by the bed of the channel to the flow. So these three are surface forces working on the control volume, and the main driving force of flow, or which is actually the body force, is given by the weight component of the weight of the fluid walking in the longitudinal direction down the slope. And if the weight of the fluid in this control volume is given by W, capital W, then the component of the body force along the longitudinal direction is given by W sine theta. So this is where theta is of course the slope, the inclination of the bottom of the channel. So it's the bottom slope. So more or less these are the forces we will be taking into account while deriving the momentum equation. Now the momentum influx into the control volume can be given as M1, capital M1 is equal to beta 1 into rho into small q into V1. So where rho is the density of the fluid, q is the discharge per unit weight, v is the mean velocity at section 1, and beta 1 is the momentum correction factor at section 1. We have already discussed about the momentum correction factor, and we know that the momentum correction factor is taken into account since we are dealing with the depth average mean velocity capital V instead of the actual velocity distribution or vertical distribution of velocity in the channel cross section. So similarly, the momentum outflux from the control volume is given as capital M2, which equals to beta 2 rho q into V2, where beta 2 is the momentum correction factor at section 2, and V2 is the velocity or mean velocity at section 2. For a steady flow, for a steady flow, the momentum equation here is given as the equation which is shown in blue, which is given as F1 minus F2 minus F3 plus F4 is equals to beta 1 q rho into capital Q into capital V1 minus beta 2 into rho into capital Q into V2. So this is the statement of momentum conservation equation for a steady flow. Remember, we are dealing with the steady flow. Now, for per unit width of the channel, if we extend these terms, F1, F2, F3, and F4, the equation can be given as the last one. Here we have analyzed forces which requires some discussion, which we will do in due course of time. For the time being, let's take it for granted that the forces can be extended like this. Now, from the momentum conservation equation, let's move on to the last quantity on we are going to derive the conservation equation for. That's the quantity of energy. So the energy conservation equation, or the energy equation, is here is given in the form of Bernoulli's equation only. We have discussed already extensively. We have gone through Bernoulli's equation quite extensively. Now here we are going to apply the same equation in context of open channel flow. Now in the diagram you can see that it shows general open channel flow, where the bottom slope and the water surface slope and the energy line slope is all are shown, and notice here that the channel has again an inclination of theta, a slope of theta. So here the normal depth is given as given by this y1 or d or y2 here, which is if we consider the depth from the inclined bottom of the channel, so the depth of the channel which we estimate will be the normal depth, whereas the vertical depth is slightly different from it. Vertical depth can be given as the cos theta component of the normal depth. So the vertical depth here is given as y1 cos theta, d cos theta, or y2 cos theta at different sections. So this is the, remember, this is the difference between normal depth and vertical depth. Normally the open channels, the slope of the open channel, all the channels that we encounter is mild. That means the typical inclination of or slope of a channel is well below, sometimes is below or sometimes well below 10 degrees. So in that case, the normal depth and vertical depth are almost becomes almost equal. So in that case, we can work with both of them. So here in this figure, let's focus on the point capital A in this figure at the center. So here at point capital A, the total energy, the total energy can be given as capital HA, which equals to the summation of the elevation head, the hydrostatic pressure head, and the velocity head. The elevation head of point A from the datum is given by capital ZA. The hydrostatic pressure head at point A is given by d cos theta, and the velocity head at point A is given by alpha into capital V square by 2g. Note that alpha is the kinetic energy correction factor, which we have discussed before, as we are dealing with mean velocity at section A. So and not the depth varying velocity. So we are introducing this kinetic energy correction factor alpha um, in the equation. So the total energy is the summation of ZA plus d cos theta plus alpha into v squared by 2g. This is the total energy. In the figure, note that the total energy line is shown by a dotted line at the top. This dotted line is of course a drooping line in the longitudinal direction, and the line drops because there is a loss of energy, of course, due to the channel resistance and some other factors. Remember the note that the total energy is constant at section A for all values of D. So it doesn't matter that what at what depth we are considering the point. So the total energy is constant for all the sections that's passing through section A, point A. So in that case, we actually, if we estimate or consider the total energy at sections 1 or 2, they can be given as H1, which is the total energy at section 1, which is the sum of Z1 plus Y1 cos theta plus alpha 1 into V1 square by 2g. And similarly, H2 can be given as Z2 plus Y2 cos theta plus alpha 2 into V square by 2g. Note here that that Y1 or Y2 are the normal depth at sections 1 and 2. So whereas in the last case, the point A was taken as in the middle of the flow cross section. Here we are estimating the total energy from the channel bottom. Also note that the term capital Z plus Y cos theta in the figure, note that the terms capital Z plus Y cos theta gives you the altitude of the water surface from the datum. So in this case, the water surface in context of open channel flow, the water surface elevation gives you the piezometric head for open channel flow. So that is mathematically here given as Z plus Y cos theta. And of course, what we discussed before, that for open channels, as open channels have normally a mild slope, so in that case cos theta can be neglected because that becomes the value becomes close to 1. So in that case, the total energy can be given as capital H is equal to Z plus Y plus alpha into V square by 2g. So the in course of the flow, there is of course some energy loss or head loss, and the head loss is given by H1, capital H1 minus capital H2, which equals to the head loss HL. This and this is actually the equation of energy conservation for a steady open channel flow, and the terms capital H1 and capital H2 are estimated from Bernoulli's equation. Now let's talk about the head loss a little bit. Head loss in open channel is mainly caused by the frictional resistance offered by the channel bottom or channel sides, and there is a secondary loss of head due to the formation of eddies, or which is called the eddy losses or foam losses. So the total energy here, the head loss HL, small hl, equals to small hf, which is the head loss due to friction, plus small he, which is the head loss due to eddy formation. Eddy formation uh, in the open channel arises due to some irregularities in the channel, due to um, secondary currents, due to irregular channel boundaries and bends and corners, etc., etc. So for a purely prismatic channel, we can consider the head loss due to eddy formation equal to 0, and in that case the head loss becomes purely frictional. So for prismatic channels, head loss is only frictional. In general, we can see, as we can see in the figure, that the channel bottom, or the bottom slope of channel, the slope of water surface and slope of the energy line, they are different. So this is a general case we are considering. So in that case, these three slopes are different. Note that the bed slope is a geometric property of a channel. So for a man-made channel, this is human control. This can be controlled by us, uh, but for natural channels, this entirely depends on the dynamics of the channel, of the river or canal, whatever dynamics of flow. So it's a geometric property, whereas the slope of the energy line depends on the resistance characteristics of the open channel. So it depends on what kind of what kind of bottom roughness or boundary roughness the channel offers to the flow. Uh, Also note that the difference of the piezometric surface, that's the water surface for open channel flow, to the energy line gives you the velocity head of flow. So in the figure we can see that the difference of elevation of the energy line minus the difference of elevation of the energy line and that of the water surface gives you the dynamic head or the velocity head at any section. So that's pretty much about the energy the energy equation for open channel. So before concluding this discussion, let's discuss something about on momentum and energy correction factors. So we already discussed and we know what are they. Let's discuss about what kind of typical values they have in context of open channel flow. Now, for so momentum or energy correction factors, normally the typical values of them are always greater than unity. So typically the value of the kinetic energy correction factor alpha is greater than the momentum correction factor beta, which is greater than 1. But practically, of course, the momentum or energy correction factors arise due to the vertical velocity distribution. So if the velocity distribution in the open channel is uniform, if the vertical velocity profile is close to uniform, remember we are not talking about the uniform flow yet, we are talking about the uniform vertical velocity distribution. So if the vertical velocity distribution is close to uniform, then the values of alpha and beta are close to unity. So more the distribution of velocity is uniform, more the value of alpha and beta is close to unity. So for large and deep channels of regular cross section, they tend to have lower values of the coefficients, whereas narrow and shallow channels tend to assume higher values of the coefficients alpha and beta. Uh, Typical values of alpha and beta for straight and prismatic channels, what have been reported in the literature, is in the order of 1.10 and 1.05. So typically, what for a fairly straight and prismatic channels, so practically we can assume that alpha is equal to beta is equal to 1 when the flow is uniform or gradually varied. So this has been a common practice for hydraulic engineers dealing with open channel flow. So that's it for the time being. Um, in the next lecture, we'll be discussing the energy depth relationships of in open channel flows. So thank you very much.